Hey guys, welcome to another video. So we're going to start a new series, the calculus area under a curve series. Probably going to go for about 3 lessons, and this is part of the Year 12 2-unit advanced syllabus. So I am planning to do a series of area and volumes videos to do with the extension 1 syllabus as well. So, but the next 3 videos focused primarily on the advanced syllabus. So area under the curve. Now, if we start there, so calculus, let's just say area, yeah. Now, I know your teachers at school and through textbooks and through other places, you already know the formulae, right, for area under the curve. So let's not beat around the bush. So let's just, if we had any sort of area under a curve, let's say between the values of A and B, all right, just to sort of develop our formulas. So this area here, we know the formula is going to be the integral between the limits of A and B of, now let's give this function, well, let's call it fx, all right? It'll be, now I'll put, instead of writing fx, can I just write y dx, right? Because y is fx in this case. And guys, so that's the formula, right? Pretty straightforward, nothing fancy there. And I think the important thing to note is, if you go to the theory of why this formula is what it is, it's basically the integral sign is almost like a sum sign, right? The sum of. And these two aspects is almost like taking the y values times dx, which is basically a change in value of x, that's dx there, and that's y there. It's basically summing up the area of little thin rectangles, right, from A to B. That's really what the formula is, which basically means that if I had an area, right, let's go maybe like that, where I'm taking the area along the y-axis, right, from A to B, then all that really changes, right, is that the area equals to integral, once again, from the 2 limits of A to B. The only difference is your area of your, really thin rectangle is now going to be x and dy as a height, right? So x dy. So whenever you experience questions that have area along the x or along the y, that's how you react to it, right? Same formula, pretty much, with x and y swapped around based on the fact that some rectangles are vertical, like the first one, or horizontal, like the second one. So nothing too fancy there. So guys, the video today, I'll just go through a number of past paper questions just to illustrate point. The next few videos, basically, I want to do one that finds the area between 2 curves, and then just some other different ones where sometimes they give you the area and you have to find an integral or something like that. So just a bit different, right? Just to show you the breadth of questions that can fall in this topic. But before I dive into the questions, if you haven't already done so, please subscribe to the channel, give the videos a like, just so people can find it when they're sort of looking for it on YouTube. So let's begin. The first, that's not the first question that I want to do. This one is, let's start off really easy, right? This is from Balcombe Hills 2014. So what do we have here? Find the area enclosed by the curve and the x-axis, right? So now, if it is as vague as that, right, doesn't tell you the limits, basically you can sort of see that the area enclosed in here is probably this area here, right? Now, one thing to note is whenever there's an area that's underneath the x-axis and you're just integrating, it's going to be negative, right? Whatever integral you find, if I integrate this, so the formula, sorry, the function in this case is y equals to x times x plus 2. If I blindly integrate it from -2 to 0, I'm expecting a negative number, right? Because it's under the curve. That's what integration does. It finds you positive and negatives, right? And sometimes the harder questions is when you span positive and negatives. If you want to find the area, you just got the absolute value of the negative part. So in this case, right, the way we're going to find this area here, right, if I integrate blindly between -2 and 0 of the function, right, so y dx, right, and just to be clear there, in this case, this guy, I'm going to sub this into here, right? Yeah, that's the goal, because to do integration, if your variable that you're integrating is with respect to x, so integrating with respect to x, I need to make this expression with expressed in terms of x, sub that in, and I should be able to integrate. Now, what I was saying was the fact that this is below the curve. If I found this integral, right, using the limits that I expressed as 0 and -2, it will be negative. So what I'm going to do, just to anticipate that, I'm just going to absolute value that to find the area, because area as a concept is always positive, right? So putting this all together, right, integral -2, 0. Now I'll expand it while I sub it in, just to make it easier for me to integrate, right, dx. So the integration step here is super easy, plus x squared. And I'll put in my limits, 0 -2. Right, there is a way of, if you know it's going to be negative, you can actually flip the limit, but I'll get there in a sec, right? That's what I tell my classes. I'm surprised that some teachers at school don't teach it that way as well, that whenever you have a negative in front, the limit's flip. It's a cleaner way of doing it, but anyway, let's just carry forward. So sub in 0. So 0 cubed on 3 plus 0 squared minus, sub in -2 with brackets, please. Very common mistake with that bracket. Actually, in this case, it does matter over here, right? Just putting the bracket there. Guys, pretty sure you can punch that into your calculator. I believe you get the absolute value of -4 and 3. Might want to verify that, which basically means your answer is 4 on 3, right? Units squared. Pretty straightforward there. Thought I'd start with one that was, not too simple, in that you do need to absolute value it because it's negative, but the integration part is dead easy. Yeah. So hope that's okay. Now, what I was saying before about that negative is, if you know your integral is going to be negative, right? And you're taking, when you sub in the 0 and you sub in -2, it's going to be minus. If you wanted to positive that, make that positive, you basically just flip the limit, right? And get rid of the absolute value, right? So if you sort of went like, did x cubed on 3 plus x squared, you want this to be, you want to make it, it's negative, you want to make it positive, you just flip the limit around, right? Like you put -2 here, 0 there, sub it in, and it'll mathematically work. So yeah, sometimes if that's the objective of making it positive, that's what you do, you just flip the limit. Easy, guys, 2 marks, Volcom Hills, done. Let's move on. Sydney Tech. Now, sometimes some of the questions that you see will not have a diagram, right? So you don't need to know what this diagram looks like, but let's see, find the exact area beneath the curve above the x-axis. I guess in this case, a tricky part is that I don't really know whether this spans, I do actually, everything about EX is positive. So for all intents and purposes, if I was to draw a graph, doesn't matter where it is, but if you were to consider drawing this, right, I would add 1 and -1. So what would that be? Y equals to 1 plus EX, 1 plus EX. Just want to see whether equals to 1 minus. Okay, that doesn't give me any insights at all. So I'm going to pretend that it's a curve, and it looks like it's a negative exponential, exponential reciprocated. No, I'm pretending it's something like this between 0 and 1, right? I guess the point of what I'm trying to demonstrate here is that sometimes you might accidentally, right, in the question, and it's meant to trap you, that the graph has positive negatives, and you're finding the area between, A and B here. If there's a positive negative, you just got to be careful that the area, when you integrate it, you got to do something fancy with the absolute values. But in this case, it's all positive. It's worth 2 marks. So I don't think there's anything fancy. So I'm just going to assume here that the area is between 1 and 0, and I'll just integrate it now. So this is interesting, right? So back in the past, I'll say the past, in the old syllabus, before 2019, a question like this given to 2-unit students is a bit unfair, because they didn't train them in the formula that is now given to them in the reference paper. And that formula is basically the integral of, if I have a derivative and a function as a fraction, right, that's ln, right? So back in the old syllabus, this was really, you know, it was sort of taught but not formalized, right? So this type of question was commonly seen in the 3-unit syllabus or the, you know, the extension 1 paper. But in 2-unit now, you're given that formula. If you can, you know, ascertain that this guy here is a function, the derivative of that is exactly that, right? So I actually have the derivative upstairs. Then quite simply, right, when I integrate this, it'll just be ln of the function downstairs plus c, but in this case, I've got limits, right? So actually, the numeric part of this question is very straightforward, right? Very, very straightforward. Let's see. Equals subbing 1, so that's ln 1 plus e to the power of 1 minus ln 1 plus e to the power of 0. Guys, that's just ln 1 plus e minus ln 2. And if I was to make my teacher happy here, I'd combine the logs, right? When you minus logs with the same base, divide, and that is my answer. Check that, perfect. Right? So mathematically, calculus-wise, super easy. Just initially, just got to be careful. Sometimes when they give you a diagram, now in this one here, it's not entirely clear, right? They should, the better questions when they state it, they'll basically tell you that it's all in the first quadrant, it's all positive, or sometimes when they're silent, the better questions, it's silent because there's positive and negatives and you just got to work it out. In this one here, it's not very clear because it's hard to gauge what type of graph that is unless you use some advanced graphing techniques that you learn in 3-unit where you sketch 1 plus ex and then you reciprocate. Guys, take it from me. That's an advanced question worth 2 marks. That's the answer. You don't really need the graph. I'm not even sure if that's what the graph looks like. Doesn't matter. It's all in the first quadrant. It's all positive. Is that all right? Integration wise. So area under the curve, if it's along the x value on the bottom, right? If it's moving along the x, then I know it's dx, right? With the function of x in here, right? The y value, which is this guy. So nothing too fancy about that. Let's move on. So Sydney grammar. All right. A trig function. Now, I just wanted to cover this base, integrating with respect to trig or doing areas with respect to trig. Not that hard. Let's have a look. Now, positive and negatives. Just be careful about that, right? Diagram. Okay. Find the total area bounded by that between the x-axis and 0 and pi on 3. Oh, pi on 3. See, here we go. So pi on 6, pi on 3, I believe. Wait. Pi on 3, is that exactly in the middle? Pi on 3, no, it's not, right? No. Is this a scale? Let's say pi on 6. 2.3, it is, right? It is bang smack in the middle. Okay. Pi on total, okay, total area. Okay. So it looks like they want the area between this bit, yeah. Let me just check that that's the case. I think that is. Now, if that's the case, right, then you can see visually, right, or if you knew your period of motion, because a full period of motion there is 2 pi and 3, so pi and 3 must be in the middle, right? So exactly symmetrical. Now, why is that important? If I'm finding the area of these 2 pink parts, they're identical. So a smart way of doing it, instead of integrating from 0 to pi on 3, I'll just go integrate from 0 to pi on 6 and double it, right? So the area in this case, right? I'm just going to take this area here, right? From 0 to pi on 6, oops, say pi on 6, and I wrote pi on 3. Of course, 3x dx, and then I just multiply this guy by 2, right? Because it's symmetrical. Is that all right? Also, just for completeness here, right? If you actually integrated from 0 to pi on 3, of this function, you're basically adding the areas of the positive upstairs to the negative. You get 0, right? Because the top offsets the bottom. So this is the way to do it. Double from 0 to pi on 6. So now that becomes a really easy integral, because the integral of cos is sine 3x on 3, right? Take out to the limit pi on 6 and 0. The 2 out here, guys. Before you sub in the limit, maybe factorize the 2 on 3 out, and then let's sub in the limit of pi on 3. So it's 3 times that. That's sine m pi on 2 minus sine 3 times it is 0. Now we know that sine pi on 2 is 1. That's 0. So very simply, 1 times 2 on 3 units squared. Simple, right? Easy, done. Yeah. All right, next one. All right, Caringbah. Now, this one here is a bit more intense, right? In that you can see for 3 marks, I'm actually, this area here is between 2 curves. So the smart way of doing this question, right, is to basically break up the question from this point here, right? So call that the blue area, and this one here is the pink area, right? And the reason why that's important is because the blue area is underneath this curve, while the pink area is underneath this curve, right? So when we break it apart, I'm going to be integrating between 2 parts. Now, the only extra point here, right, is that I currently don't really know, well, this is pretty easy to know, right, what this limit is, right? This limit here. But I mean, if you were to solve between these 2 points, guys, 1, 1, you know, is the point of it. That coordinate there is 1, 1. So then when x equals to 1, right? Yeah. So why is that important? Because then the blue limits would be, the area of the blue area would be between 0 and 1, and the pink area would be between 1 and, well, 3, right? So let's set this up. So total area, right? For the blue one, maybe I'll use the blue pen here, between the limits of 0 and 1 of this function here, it is always, in this case, all the questions we've done so far has been dx, because it's always been along, moving along the x-axis, right? Now, I need the y value, right? So what I'm going to do, right, is just to put in x cubed in here, right? So this guy goes in here. Yeah, makes sense. Plus the area of the pink, which goes from 1 to 3 of this y value of root x dx. Yeah, so nothing too wow about that. Now, there can be harder questions, right, where finding the point of intersection takes a longer time. You might have to solve quadratics and et cetera, But this one here, you know the cubic 1, 1, you know square root 1, 1, right? Point of intersection by observation, quite easy to find, guys. And now it's just the integration algebra part. Add 1 to the power, divide by new power. These limits here. This one, ooh, that's power 1/2, right? So this guy here, power 1/2. So when I add 1 to the power, divide by new power between 3 and 1. Yeah, just looks like uglier numbers, right? So let's have a look. So this one, something 1, so it looks like it's 1 to the power of 4. You know what? I'm just gonna, let's take out the constants before we sub it. Let's clean this right up before we subbing numbers, right? Now, divide by, so reciprocate that fraction. 2 on 3 comes over here. X to the power of 3 on 2. All those numbers aren't going to be pretty. Yeah, aren't going to be pretty, but let's see where it takes us. So this is 1/4. X to the power of 1, so that's 1 to the power of 4 minus 0 to the power of 4. Pretty simple. 2 on 3. This is 3 to the power of 3 on 2 minus 1 to the power of 3 on 2. What's that? Root 27. Root 23, is it 3 root 3? Okay, that's a quarter. All right, so if you actually cleaned it up, you know, like this would be a quarter plus, that's, is it root 27? Yeah, root 27 is 3 root 3, so root 3, that's like 2 times root 27, is it? Is it 3 root 3? 27, 3 root 3, right? And it cancels out with 3? Yeah, cancels out with 3, and it leaves 2 root 3, and then minus 2 on 3. Guys, I think if you common denominated everything, the answer would be hopefully 3. What's 1? Where's my calculator? 1/4 minus 2/3 minus 5 on 12. Yeah, maybe I'll just leave it like this. 2 root 3 minus 5 on 12. Piece of cake. I put brackets around that. Oops. Clean up brackets. Units. Squared. Okay, nothing too hard about that. Hopefully, I mean, the hardest part there seems to be like the thirds and the indices there, but that's how you do it. When there's 2 areas, do it one at a time, right? Pretty straightforward. So this video, hopefully, you know, it's quite introductory, but I do want to do one more question. And the last question, look, I've seen it so many times. Whenever my students do it, some of them react well, some of them don't. So let's see how we go. So many iterations of this question, right? Where you have a log question. You know? Now, the thing about integration is, especially in advanced and extension 1, is that you can't integrate every function. In fact, even in 4-unit extension 2, you can integrate more, but you can't integrate everything. In this case, it's a clear demonstration of the fact that if you can't integrate every function in Year 12 advanced maths, there must be a different way to do it. So let's have a look. In this question, it says, can you please consider a graph? This is the area I want. Okay, pretty, you know, okay, pretty straightforward ask that they're asking you to do there. All right. They want this guy. So now let's see. If they want this guy, okay, between that, okay, perfect. So now I'll tell you why this is harder, because this one here looks easy, looks quite innocent. The area there is between the limits of, now, what's this guy? When x equals 0, sorry, when y equals 0. Yeah. I don't actually know what that is. I think it might be a half, but let's have a look. So when y equals 0, yeah, 0 equals to ln 2x, exponential that becomes, yeah, 2x, and then x equals a half, okay. So between a half and 2 of ln, I'm just going to replace log e with ln 2x dx. Now, looks innocent, but then you go, well, wait a second. You can't integrate ln 2x, right? That's not something that's common or doable, right, as part of the advanced course. It is doable as part of the extension 2 course, right? You can use by parts, right, to do this, but we can't do it. We can't use by parts in 2-unit, right? So what do? In this question, it's a classic case of there must be another way, right? And that other way is to do it like this. Can you see, right, that if I take, to find the blue, I'm gonna find the area of this rectangle, which is really, really easy, right? Because it's like the base is 2 units. And the height is whatever the y value is, right? So if I sub 2 into the x value here, right? ln e of 1, right? ln e of 1. Now let's see, right? To find the height when x equals to 2, y equals to ln. Oh, sorry, not 1. Sorry, I thought it was dividing ln 2 times 2, so ln 4, right? ln 4, pretty straightforward. That's ln 4 as a height, which basically means this is 0 here, and this is, you know, I just remove this. Let's clean this right up. So this is 0. And this is ln4, which means the height of this rectangle is ln4, right? So let me actually write height. Yeah. All right. Now, if I can find the area of the green, which is a rectangle, to find the blue, all I got to do is subtract this area over here, right? Now, feels a bit convoluted, right? Why am I doing green minus pink to get blue? Because I can actually integrate the pink, you'll see in a second. Right now, I can't integrate the blue, can't do it. Need another way. Area of the green is easy, 2 ln4, right? Area of the pink, let's explore, right? Let's explore. Now, so this one here, just be clear, guys. This guy equals 2, can't be done, right? The blue can't be done. So instead, right, this is how I'm going to play it out, guys. Area of, now I would use diagrams to help you, right? Let's go. Maybe I won't do area. I'll do area of this guy. Yeah, my students, this is what they see me do. Area of this guy equals 2. Green rectangle. Yeah, I like diagrams. There you go. Minus area of, let's try to draw this. Not very nice. The pink, right? Pretty straightforward. Now, the green is easy. Base times height. So that is quite simply 2 times ln4. Done. Job done. Minus. Now the pink. We know the limits already, right? It's 0 to ln4. Now, function, because it's along the y-axis, right? Yeah, remember, if it's along the y-axis, it's dy, and I need a function here, right? I need a function here in terms of y. Right now, the function is in terms of x. So what do I do, guys? I need to make x a subject, right? So if y currently equals to ln2x, exponential both sides, ey equals to 2x, x equals to a half ey. Now, that's cool, because if the function is exponential functions are really easy to integrate. Log functions, hard. Exponentials, dead easy, right? Dead easy. So what I want, guys, is this function to come in here and go a half ey, right? This guy in here. And this is my game. The green is done. The pink, very easy to integrate. You just gotta, now your teacher's probably gonna need you to do a bit of log laws to clean that up, but not too bad. All right, let's clean this up. All right, so that green part is 2 ln4 minus, now this here, pull out the half. Guys, integrate ey, well, it's ey. Yeah, ln4 upstairs, 0 downstairs. Yeah, nothing too fancy about that, guys. Let's sub it all in. 2 ln4 minus half e ln4 minus e0. Yeah, let's see if this works. Looks like half minus 1. Have I done something wrong? Have I done something wrong? No, I think that works. Oh, yeah, that works. So let's see. So that becomes 2 ln4. Sorry, I just had to look at the answer, and I did something to simplify the logs, but I don't think it's necessary. Hey, exponential and logs are mutually inverse. So when I e and ln, they cancel out, that becomes 4. And that is 1. It's actually quite nice, 3 on 2, right? Because that's 3 and then on 2. Yeah, that's the final answer. Now I'll tell you what they did in the answers. You tell me whether it's significant. They basically made that into 2 squared and brought down the 2, made it 4 ln2. Don't know why. All right, guys, that's the answer. Yeah, that's the answer. Sorry, I won't box that. It just convolutes it. How's that? So this log graph is so common. Sometimes they change the log function, in this case 2x. Sometimes they do something different, but the concept is the same. You can't integrate, in advanced maths at least, or extension 1 for that matter, ln. So then you switch it, right? You find the area of the box and you minus the pink one in this case, which is an exponential function, which you can easily integrate. Guys, hopefully that was okay. that's the first video on the advanced series of area. I'm planning to do 2 more. Next one that I'll do area between 2 graphs. And then the third video, just something different, right? Some other past paper questions that you see. And then the aim is to do a series on extension 1, area and volume. Guys, if you like that, give us a like, subscribe to the channel. I'll see you guys later.